Good morning. So we are going to talk today about stability, and we are going to talk about that rather briefly. Stability is a very, very extensive subject. I mean, it's extensively discussed in controls and dynamical systems and things of that sort. And feedback theory, there are more advanced classes that actually talk about this, quite a few of them going forward. But we'll start basically introducing the concept of stability. And the first question is that what do we mean by stability? So we are talking about stability. So think about a situation when you are dealing with a system, let's say an LTI system, a linear time invariant system. Let's say right now you're talking about a single input, single output system that has an impulse response h of t. Right? This should be a very familiar picture by now for you, this view of a system, a box that takes an input and produces an output. So the question is that, what does it mean what do we mean by stability? Can you think of a measure of stability when you talk about it? So what does it mean for a system to be stable or unstable? Can we say something in terms of the behavior you expect from its impulse response? Can you think of something that you would say about its impulse response to determine whether or not it's stable? Yeah.
If the impulse response ultimately converges to zero,
It's so if the impulse response, the answer was if the impulse response ultimately converges to zero, the system's stable, and that's a good way of analyzing it. That's basically what we call the essentially absolute stability of the system, which means that if you look at the system and say, well, okay, if this is the impulse response and the limit of the impulse response when t goes to infinity, if that limit is zero, meaning that the impulse response eventually converges to zero, it dissipates, it diminishes. This system will be stable because its output cannot explode for finite input, right? So that's basically what we call the BIBO stability, bounded input, bounded output stability, in the sense that for a bounded input, you will have a bounded output. Now, how about instability? What do you call, so this is called stable. So based on this, can you think of something that would be a definition of a system being unstable? How do you say a system is unstable? It kind of should be the opposite of that, right? So saying that limit of h of t when t goes to infinity after you wait a long time is infinity, or, well, it's infinity. Meaning that the impulse response blows up. So even if you hit it with something that has finite amount of energy or charge, it can grow without bounds, and it can blow up. Can you think of a system that behaves this way? Can you give me an impulse response that we've seen that behaves like this and is stable? Yes? E to the negative t, right? E to the negative t u of t. Something like that. This is an example, right? Can you give me an example of something that behaves like this? Yes? E to the ut u of t. Yeah. And that's something that blows up. Now, these are not obviously the two only possibilities, right? There's a third possibility, which is what? Say again? It's constant, right? So some non-zero quantity. So if the limit of t when h of t when t goes to infinity is some constant, then, so by the way, this is unstable. The second one was unstable when it goes to infinity. The last one, when the limit goes to a constant, is non-zero, is what? It's called marginally stable. So that's what we call it, marginally stable. Can you give me an example of this? Or actually more accurately, if you want to make it even more accurate, you need to say this limit is smaller than, or the absolute value of this limit is smaller than or equal some c. It's bounded to some value. Yeah. So that's the question of how do we define this? There are different definitions of stability. So there are two different stabilities. One is called BIBO, or bounded input, bounded output, which for short is BIBO, BIBO stability, which means that for a finite input, you will not get an infinite output at infinity, right? This is what we're talking about is called BIBO stability. There's another measure of stability. There are lots of different measures of stability, really, but which is called absolute stability. Absolute stability, it means that the system will eventually converge to this. So this would be considered unstable under absolute stability. And there are different ways of looking at that and analyzing it. And there are many, many different criteria and ways of determining if a system is stable or not. But it would take some time to, we won't do it here. We will just look at one very simple one, and then the rest of it would be covered elsewhere. So marginally, can you give me an example of a marginally stable system? Or can you give me two examples of marginally stable systems? Okay, good. Well, I consider them more or less similar things. So sine. So if the impulse response is, cosine of omega 0 t u of t, right? This is something that's bounded, but it's not necessarily doesn't go to 0. Can you give me another one? U of t itself, right? So u of t also is an example of that. A system whose impulse response is a u of t. So an ideal integrator. That's an ideal integrator, right? A system whose impulse response is a step is an ideal integrator. So an ideal integrator is not technically stable, it's marginally stable, if you will. And it's not absolutely stable in that sense. Okay, so that's fine. So that's a definition. That's a definition that kind of makes sense. But let's relate it to the things that we know. So let's say you're dealing with a system, let's say who has a system operator of the form 1 over p minus s naught. So it has a single pole, if you will. And if you look at that, obviously you have a system function, which is going to be s minus s naught, 1 over s minus s naught, which we determined last time, right? We talked about the system function being essentially the coefficient in front of the e to the st when you as a response of the system to e to the st. So this response, if you look at that, if this is the system function, it has a single pole, it has a single root, right? So the question is that, is it stable or unstable? First of all, what is the response of the system? What is the time and what is the associated impulse response for this? What is the impulse response for this system operator or system function? E to the s0t u of t, right? So what we are trying to determine is to determine what's the magnitude of this thing. So what is the magnitude of this thing? Let's see. So we are looking at this, and now S naught is a complex quantity in general. So it has we can write it as sigma plus j omega, where sigma is the real part and omega is the imaginary part. So and both of these numbers are real numbers, sigma and omega, which makes S naught a complex number. So if that's the case, we can plug that in, and what do we get? We get e to the sigma t, e to the j omega t, u of t. So if I'm interested in the magnitude of this thing, so if I'm interested in magnitude of h of t, I have to look at the magnitude of this and magnitude of this times u of t, magnitude of u of t, which is u of t. So what is the magnitude of this part? E to the j omega t. What is it? Yes. 1. Why is it 1? Say again? Okay. Yeah, that's one way to think about it. Yeah.
So it's sine and cosine.
Right, you could write it as cosine and cosine. That's another way. So what is this? You can write it as, so you can write e to the j omega t as cosine of omega t plus j sine of omega t. And the magnitude of this thing is this squared plus that squared, right? So this is something that you should think about this way. E to an imaginary number always has a magnitude of 1. If it's purely imaginary. It's a unity vector that's rotating. It can be pointing in different directions, but it's always a unity vector. The size of that vector is captured here. So you can see that if you have a complex quantity, if you are looking at it in a polar coordinate, its angle is captured here and R is captured in this one. And we'll use this extensively later on. But okay, so this is 1. So it's basically e to the sigma t u of t. So what does it tell you about stability? So what can we use so what is the thing that determines the stability of the system? Is it this omega or the sigma? Which is the real part, right, of the root, not its imaginary part. So what is the real part? So what can you say? So what values of sigma? So if sigma is, for what values of sigma would this be stable? Say again? Negative. So if sigma is smaller than 0, then h of t, the limit of h of t when t goes to infinity is going to be 0. So it's stable. And if sigma is greater than 0, what is it going to be? Unstable, right? Because the limit goes to infinity. So it's going to be unstable. And if sigma is 0, it's going to be marginally stable, right? Because its magnitude is going to be 1 in this case. So what does this tell you? It appears that, based on this, there's something that's unambiguously, you can tell unambiguously, at least for this kind of, if you have a single pole. The response of the system is unstable if the pole is where in the complex plane. So this is the S plane, right? This is the sigma j omega plane, right? So for poles where on this plane, I have a stable system. For the left half plane, right? Left half plane. You will see LHP and RHP a lot later on, because this is very important. So you can see it says a left half plane pole or right half plane pole. And then we'll talk about left half plane zeros and right half plane zeros, and you will see that they have a different kind of behavior than poles. So if you have a left half plane pole like that, then the system is, if that's the only thing you have, is stable. And if you have a right half plane 0, the system is unstable. Now, if you have a pole right on the j omega axis, where sigma is 0, then it sounds like you have a marginally stable system, but we have to look at it a little bit more carefully now. So let's look at this a little bit more general, because the poles, so what we did so far was for a single pole. What if you have multiple poles? So what if you have in general a system whose operator is 1 over p minus s0 to the m, which corresponds to a system function of 1 over s0 to the power of m. So what is the impulse response of this system? You should know it by now, right? So h of t is what? Does anyone remember? We did this catalog. Say again? T to the m minus 1. Okay, yeah. M minus 1 factorial e to the s0 t u of t. Yes, that is correct. So that's what you get, right? Now, how about this system? what values is it stable for and what unstable? So let's look at the magnitude of h of t, and let's write S naught as sigma plus j omega. If you do that, then this becomes just basically t to the m minus 1. Well, it's positive t, so for positive t's, I don't need an absolute value. And then this becomes e to the sigma t, e to the j omega t, u of t, and then this magnitude of this and magnitude of that, which basically collectively give you, this basically gives you a magnitude of 1, so that's what you're left with. So is it stable or unstable? For if the sigma is smaller than 0 at infinity, is it going to be 0 or non-zero? So it's a competition between an exponential and a polynomial. And in the competition between an exponential and polynomial, the exponential always wins. Eventually. It's kind of like gravity, right? You can make an airplane, but gravity eventually wins. You come down, finally. So exponential wins, and since exponential has a negative coefficient, it's the one that goes to 0, so this is going to go to 0. So limit of t going to infinity of h of t is going to be still 0. So still the same thing is true. If you are on this S plane, where this is sigma and this is j omega axes, if you are in the left half plane, if you have poles in the left half plane, or let's say right now we have talking about 1, but you can have more, then the system is, so if you have this is stable. It's a stable system. Now, how about when sigma is greater than 0? Now, this is no contest because both of them are trying to go to infinity anyway, right? So they help each other. Okay. Now, and then if you have sigma equals 0, what happens? Now, this is the interesting part. This is why we really did all of this. So what happens at sigma equals being equal to 0 when t goes to infinity of h of t? So what's going to happen? Well, if sigma is 0, this is going to be what? This is going to be 1, 2. So none of this is, so you have u of t, and then you have t to the m minus 1. So is it stable or unstable? Well, it depends on m, right? So this is infinity for m greater than or equal to, or let's say greater than 1, and some constant, in this case 1, bless you, for m equals 1. Right? So for m greater than 1, is it stable or unstable? It's unstable. And for m equal 1, it's marginally stable. So in this picture, if you're in the left half plane, are you stable, or if your pole is in the left half plane, or if you have poles only in the left half plane? Is it stable or unstable? The system is stable. And then if you have a pole in the right half plane, how about that? The system is unstable. And then how about if you're on the j omega axis? It's marginally stable for single pole and unstable for multiple ones. So you have a criterion for stability, right? I mean, in the sense that you can look at the system and say whether or not it's stable or unstable. So, but by the way, let me ask you a question. What if you had multiple poles in different locations? So let's say the system has, let's say, a pole here, and a pole here. Is it stable or unstable? So basically, I'm talking about a system that looks like S plus 2, S plus 1 in the denominator in the system, and S minus 1. Is the system stable or unstable? Okay, so let's take a poll. How many of you say this system is stable? Nobody. How many of you say it's unstable? Everybody. Okay. Well, you're right. Why is it unstable? Right, because there would be one term that goes to infinity, right? It takes one crazy guy. It takes one stable person, right? To destroy a lot of things. Okay, so and the other way to think about it is that you can do it as a partial fraction expansion, right? You can have like this. And then they would have some coefficients, right? I don't know, K1, K2, K3, right? And then, so basically your response will consist of this response, which in this case would be something like e to the negative 2t u of t, some K1 times that, plus this response, which is K2 e to the negative t u of t. Both of these are going to go to 0 at infinity, plus this guy, which is basically K3 e to the t u of t, which explodes. Yes?
In your red statement, you said unstable for multiple poles, but if n equals to 1, it could be marginally stable, right?
Well, that's what I said for single pole. Here, you see, I said marginally stable for single pole with my cryptic handwriting, and then oh, I guess should be or, really, logically. Or unstable for multiple poles. So that's fine. Yeah. So what if you had something that was of this form? Let's say a slightly different form. So let's say you had this, and then but the numerator was even larger. Let's say it was like S4 plus some S3 plus some stuff, right? So on and so forth, right? Something. If you had something that was an improper, what did we need to do with that? We need to make it proper. How do we make it proper? Divide. Do a long division, right? So if you did a long division, then what would happen here is that you will have also a couple of additional terms. You will have some constant term. I guess the way I wrote it would be A1, plus some other term, let's say some S term. I think it would be 1 in this case, but it doesn't matter, the coefficient. Something like that. So what would these do? Is the system stable or unstable now? So let's see. What happens to the response? What is the response of this? What is the impulse response of this? An impulse with a, yes, exactly. Right. So it scales it by A1, so it's an impulse. What is the impulse response of this system? Doublet. Yes, right? So is this stable or unstable according with our definition? Look at this and think about the definition. Stable or unstable? Okay, so let's take a poll. How many of you think it's stable? Okay, couple of people. Keep the terms before. All the terms. Stable or unstable? Nobody's saying stable. Okay, unstable? Okay, why is it unstable? For it to be unstable, at what time does it matter? What is the time where you evaluate things at for evaluating stability or lack thereof? Infinity. What's the impact of those last two terms, those new terms at infinity? Nothing. They do something, right? They have an initial reaction that may be a little bit violent. It doesn't mean that they're unstable. right? You give somebody a little bit of a shock, they do some crazy thing, maybe immediately do something out of the ordinary. It doesn't mean they're unstable. It's a question of like once things settle, how they behave, right? So the same thing. I mean, nothing happens at infinity to those terms. Actually, this part of the system is nothing but a kind of like a scaling system. Whatever you put into it, it just scales it by a1, multiplies it by a1. It's actually pretty rational character, right? The other one just takes a derivative, it gets a little bit excited. It goes away immediately, right? It's this kind of stuff that's dangerous. Well, dangerous is not the right word. I mean, sometimes you want to make a system unstable. Can you give me an example when you want to make a system unstable? A useful system. Yes? Say again? Nuclear fission. I was thinking more socially positive, but okay. There are things that are, because you know, in nuclear fission, you don't, in a nuclear reactor, you don't want to have a term like this, because then it's a nuclear bomb. Say again? No, okay, yeah, you're right. I mean, well, sure, yes, that's an example, if that's what you're going for, that's true. So let's think about an electrical system. Man, you guys are really into it. But how's EMP unstable necessarily? Electromagnetic pulse. It's something that basically paralyzes all the electronic systems. Right. Okay. Something simpler. Well, at least you try. It starts off like that, but then eventually something blocks it. But an oscillator, right? An oscillator is a system that needs to grow its amplitude, because when you turn it off, turn it on, it doesn't have an amplitude, and you want to turn it on, and if you want it to have an amplitude and input and signal, and there are tons of oscillators, everything. You guys probably are carrying like probably 50 of them in your pocket right now, in your phones at least, and there are different things that generate different signals and things of that sort. So that's when you try to make a system unstable. A latch in digital circuitry, when you want to store data, it's the instability that gives you the ability to store data, because if you have two nodes, and then one of them goes up and the other one goes down, and they reinforce each other, they get stuck eventually, the supply voltages. But it's that instability that allows it to maintain its state. It gives it the memory, the single bit. So instability is a useful thing if you properly use it. In fact, for a lot of, for example, like agile fighter jets, they're intentionally made unstable by design. The mechanical system is unstable because it makes it very agile. Then they put an electronic system on top of it to keep it, to make it stable. But then the good thing about it is that since you have a stability that has a knob, you can turn it on and off or increase or decrease the amount. If you wanted to maneuver very quickly, you can think about it this way. You take the yoke off, and then it just basically starts going in one direction, and then you kind of like say, okay, stay there. Control it and keep it there. That makes it much faster. Positive feedback is a lot of time used to enhance system performances, which is basically something that can give you instability. So stability is discussed in extensive details later on. I mean, in different contexts, in circuits, in control systems, in mechanical systems, all of those. Stability is very, very important. It's just you have to think about it the right way. So the key to this picture is, so can you tell me, if I give you a picture, what is the criterion you would use? If I give you a whole bunch of poles and zeros and things of that sort. So if I give you a picture like this, just the one that I drew, is this, I don't know, how do you determine if it's stable or unstable? So those are where the zeros are, those are where the poles are. Is it stable or unstable? How many people say it's stable? How many people say it's unstable? Yeah. Why is it unstable? Yeah, there's still one element, right? Here. How about the zeros, right? Because this element, think about it. This one is this like something like that. So when you do the partial fraction expansion, that's the one that blows up. How about the zeros? What's the impact of the zeros on the stability? Nothing. Why not? Correct. That's correct. What I just did. I mean, they just disappeared, right? Exactly. Right? When you do the partial fraction expansion, the zeros disappear, or partially disappear at least. So the zeros do not tell you anything about the stability per se, this kind of stability. They tell you a lot of other things about the behavior of the system. Now, this is also something else that's interesting. The zeros can change when in a real system when you change the location of the input and the output. The poles don't, which makes sense. Poles are the natural frequencies. Zeros should depend on not only just the system, but also at the choice of the input and output. So they're in that sense, as far as stability is concerned, they are less fundamental. So if I had a zero on the right half plane and no pole there, is it stable or unstable? It's stable, right? So what is the criterion? Why don't you articulate the criterion for stability? If I give you a plot of, if you know where the poles and zeros of a system are on the S-plane, what is the criterion? Yes. Sorry. So I think you had your hand up before she said something. She uttered something. So you first and she second.
For it to meet the criterion of absolute stability, all
These are Bibo stability. Huh? These are Bibo stability. Bounded input, bounded out. Absolute stability is different.
Okay. So then for Bibo, then everything, all of the poles must be less than equal to zero, and then if they're equal to zero, then like the polynomial like in front of them needs to be of like basically needs to just be a constant.
All the poles need to be so you're saying that all the poles need to be on the left half plane, or if they are on the j omega plane, what about them? They can't be what? They can't be they can have a multiplicity essentially. So this is stable, right? Or marginally stable. It doesn't blow up. But this, if you have two of them on top of each other, will be unstable. So let me throw you another one, which is an important case actually. It's a little bit of a curveball, but it's an important case. What is it, stable or unstable? Why? But they don't have the same j omega, right? Yeah, but here's the thing. What is the response of these are, let's say, complex conjugate pairs. What's the response of a system with those two poles? Yeah. It's a cosine, right? So they're marginally stable. So they have to be really dead on top of each other. So if you have two of them, two pairs, then it's unstable. But with one pair of complex conjugate ones, they're not. Fair enough? So now the question is, fine, okay, so we know the criterion. How do we determine if something, if I give you a polynomial, let me give you a polynomial, right? Let's say, let me give you two polynomials. S4, okay, s to the 4 plus 10s to the 3 plus 35s squared plus 50s plus 24. So let's say this is your denominator. So let's say I have given you a transfer function that has this as a denominator. So this is d of s. And I have given you another one, d of s, which is, let's just for the sake of argument, s cubed plus s squared plus 4s plus 30. So let's say you find the system transfer function and you get this in the denominator. Can you tell me if the system is stable or unstable? Because the denominator is the one that matters, right, of the transfer function, because that's where the poles are. So if I show you these two, can you tell me if it's stable or unstable? For determining whether or not it's stable or unstable, what do you need to do first with these polynomials? You need to factor them, right? You need to know what the poles, the roots of this polynomial. How do you factor this? It's not easy, right? How do you factor this? I mean, there are ways to factor these, but it's just not necessarily a fun exercise to do. So what do you do if you arrive at this? Yes?
I mean, like all the coefficients are positive.
Okay.
It has to have been composed of like a bunch of S plus SI terms where like SI is greater than 0.
So that's an interesting statement. So he says, since all the coefficients are positive, it must have consisted of a bunch of S plus some positive things. So your statement is that both of them, they have all S pluses, so basically they are all have negative roots. All the roots are negative. Is that what you're saying? Is that true? Is that true that you will get only positive coefficients here? You get positive coefficients only if you have positive roots or negative roots, or yes? Oh, you did it on mathematical or something like that? Okay, root of negative 3 is fine. Root of negative 3 is fine, right? Yeah. So that is true. It has one of the roots is negative 3. But root of negative 3 is what? Root of negative 3 is S plus 3. So that's not a problem yet. It doesn't contradict what Adiyut said, right? So what is it, how do we know? Yes? Say again? Could you speak up, sorry? Can you have, so the question is, can you have complex conjugate pairs that would produce real positive coefficient? Is that true? You can, right? But does that mean that those roots are necessarily all negative? Real parts? You have to have negative real parts, right? The real part of the root is what determines which half plane you're in. So you wanted to say, Jennifer, you wanted to add something? Or?
No, I was going to say the same thing.
Okay, good. All right, fine. Any other comments or thoughts? So what do we do? What do we do? Is there a way to tell whether or not this has poles in the right half plane or not? There are actually many different ways to do this. Many of them are called different criteria for stability. Well, I'll show you the simplest, probably the oldest one. It's one way to see something, and then there are many, many other ways of doing this. So this is called the Hurwitz criterion. The spelling of Ruth, I think. Yeah, Hurwitz. But that statement is not true. So the statement, just because these coefficients are positive, it doesn't mean that all the roots are negative. Example was that, for example, you can have a pair of complex conjugate poles. Yes?
What about all roots are not positive?
Okay, so if one of them is negative, so roots or coefficients, sorry.
The roots.
So what if they are not all negative?
Like if you make the thing, or you make the rule so that it's like not necessarily all negative, but just like non-positive. So they could be on the line, or they could be on the other side.
Oh, okay. So the question, so then we know what to do with them, right? If you get a root like that, well, those kind of roots are actually easy to identify, because for the root to be on the j omega axis, right? If you have a root on the j omega axis, what happens is that then you can easily look at it, see if it's duplicate or not, and that would tell you whether or not you have a marginally stable or unstable system. But you need to find out whether or not you have one, right? I mean, so that's the question. So how do we do that? Short of factoring it. Because you may be able to factor this, but if I gave you like an 8th order one, good luck. Or even with this one, good luck. Can anyone factor the first one? Yes.
I think you can like try different things. Like you have to try like 9 things at the most.
9 things.
To get the first factor, because
I have to try. You say I have to try 9 things at most to get the first factor. How?
yeah, so if you say the root is like, or if you say one factor is like s plus 9, then you like do it for all those things. And then, like,
But you're assuming that the factor is an integer, the root is an integer.
Oh, okay, true.
Right? It's in general can be real. Minus. So I guess, yeah, Param is saying that -1 is one of the roots. He's right, actually. One of the roots is minus, or like basically, -7. I don't think that is, but okay. So that is true. I mean, one of the roots is 1. Yeah.
Is it 1, 2, 3, 4?
Yes. Garrett, right? Yeah. Yeah, he said Garrett says it's 1, 2, 3, 4. I mean, that was a good guess knowing me. Huh?
The sum of the roots is 10. The product is 24.
Oh, okay. So what are the roots for this? Any thoughts? So this is basically s minus 1 squared plus 3. Squared, 3 squared. So, yeah. So the roots, what are the roots of this? You can write it also as s minus 1 plus 3j, s minus 1 minus 3j. Right? So that's the factorization. I mean, this was not what I was going to ask you to do. It's interesting that you could factor it, or with some help, I guess you found the factorization, but which is good, but you generally can't do it. But okay, that's good. So wait a second. So what do we expect from these two? Which is it stable or are they stable or unstable? If those were the denominators of a transfer function, would the associated systems be stable or unstable? First one, is it stable or unstable? Stable. Second one, is it stable or unstable? Unstable, right? Because it has two complex poles on the right half plane, complex conjugate pair. So that's unstable. But it's not easy to look at this and say that right away, right? And if I had made this a little bit longer, if I had been mean and multiplied that by s plus 1 and s plus 2 and given you a fifth order one, it would have been a lot more difficult to see that. Maybe I should do it next time. Just kidding. All right. So, but in general, how do we do that? So there's a criterion. There's a theorem that was basically shown by these guys. Now it's an algorithm. It's a way of calculating things. So if you have a polynomial that's in the form of a n s to the n plus a n minus 1 s to the n minus 1 all the way to a1 s plus a0, the Hurwitz criterion is applied this way. So it's just, I'm going to describe the algorithm without proof here, but you can always look up the proof. Many places. It's not that difficult. So you start with the highest order coefficient, an, and you write every other coefficient. So you skip 1, and then you get an minus 2, an minus 4, all the way down. And then you start with the next one over, the first one that you skipped, an minus 1, an minus 3, an minus 5, and so on and so forth. So you write them under each other. Then you calculate this times that minus this times that. Right? And divide it by this coefficient. So in other words, and that would become your Bn. Then, and you write it underneath. So Bn. So Bn, B sub n, is an minus 1, an minus 2 minus an times an minus 3 divided by an minus 1. And then next one over, to get the next bn, or bn, I don't know, bn minus 1, you do this times that minus this times that divided by this coefficient. So you start with the first column. You always have one first column as one part of it, and then you go down to the next column, and then you do this cross multiplication and subtraction, and you write it there. So it will be n minus 1. In this case, it's going to be an minus 1, an minus 4 minus an minus 3 divided by an minus 1. And you keep doing this till you run out. And if you're missing a coefficient, for example, it means it's 0. So you keep going, and then you fill up this table. And then you repeat this procedure now between the second and third line. So now you go again, the same deal. So you go this plus that, this times that, minus this times that, divided by this. And that would become your Cn coefficient. So Cn coefficient, so Cn is going to be Bn times An minus 3 minus An minus 1 times Bn minus 1 divided by Bn, and so on and so forth. And the next one over is going to be this times that minus this times that. That gives you Cn minus 1. And you keep doing this till you run out of everything and you get 0. And when you do that, so now after you've done this, you look at the first column and see how many times it changes sign. The number of sign changes the first column equals to the number of right half plane poles or roots. So this sounds pretty complicated. Let's do a couple examples for it to become clear. Yes?
In the Bn minus 1 equation, is it supposed to be An minus 1 An minus 4?
Yes, An. Sorry, I'm sorry, say again? This one? In this one? This one. It's An minus 1 times An minus 4 minus An times An minus 5. Yes. Yes, thank you. It's this one. Thank you. That's correct. Okay, any other comments or questions? No? All right. So let's apply this method to these two examples, right? So example 1. You know what? So I'll let you guys do it. And I will help you. How about that? Daniel, do you want to start? Start with the first one. Just write the coefficients. Tell me what the coefficients are for the first row.
1, 10, 35, 50.
50.
So sorry.
Second line, 110?
Wait, no.
No, you have to skip, right?
Yes. 35 and then 24.
35 and 24, right? So you do every other one.
Yes.
And then second line is
10, 50.
10, 50, and that's it. Basically, it means that this is 0. If you don't write it, it's 0. Okay, so now what's the first step? How do I calculate this coefficient? Tell me what it
So like take the determinant.
it's not a determinant, so don't let it confuse you. So go, it looks like 1, but it's not.
Okay, so we take 10 multiplied by 35 and subtract it from 1 minus 50.
Exactly. So it's 10 times 35 minus 1 times 50, which is 350 minus 50 is 300 divided by?
Divided by 10.
Which is give you 30. Okay, how about this one? It is going to be what times what? Just tell me. Look, those orange arrows.
So
10 times.
10 times, oh gosh, is it 35 again?
No, so you see, this multiplies by that. The next one over. So it goes 10 by
10 by
24 minus 0 times 1, which is 0. So it's 10 times 24 divided by 10, which gives you 24. Now there's nothing further down because these are both 0. So it would be this times 0 times 0. So that's it. It stops there. Yes? Huh? It's okay? All right. Good? We're good? All right. Okay. So now, do you want to do the next line? Because we're almost there. Why don't you I'll let you finish it. Okay. So same deal. It's the same. Repeat the same procedure essentially. Now, forget about the first line. Go with the second and third line.
Okay.
So what do you do?
So 30 times 50.
30 times 50.
Which 1500.
1500.
And subtract
and 240, so it's like 1260, right? So divided by 30, 12 gives you a 4, and 6 gives you a 2, so it's 42, right? Now, how about this one? Do you get something here? It would be this times that minus this times that. So these are 0, so it's 0. So just leave it open. Now, is it going to be 0?
No. Sorry. It's going to be 42 times 24 divided by 42, so 24.
24. Now it's going to be 0.
Yes.
Because this is 0, 0. Done. So you stop here. So how many times did it change signs? The first column. Nothing. 0 times. How many right half plane poles do you have? Nothing. 0. So now let's do the other example. So I'll let someone else do it. Okay, Max, do you want to try that?
Sure. So you start with
What is the first row?
1, 4, and then the second row is 1 and 30.
1 and 30. Okay, so this is even simpler, right? I'm saying that this is even simpler than the other one. Yeah. So what is this number?
4 minus 30 over 1, so that's
Negative 26. And what is this one? It's 0 because these are both 0. So you go to the next one. What is that?
Negative 26 times 30.
Negative 26 times 30 minus 0 divided by negative 26 is 30. So how many times did it switch sign? Right? Everyone's good? Do you follow exactly what happened? Okay, what? Good. So it claims that it has 2 right half plane poles, which it does. Yes?
What do the sign changes actually mean?
What do those sign changes actually mean?
Yeah, like how did this person come up with this?
Okay, that's a good question. So how did this person, or there are 2 people actually, come up with this? It's a mathematical theorem. I mean, so what happens is that when you look at the proof, you will see, basically when you dissect these products, you will see that you need to calculate these kind of things to see how each one of them relates to the next one over. So you have to write actually the expressions and what you see. So I can't give you any meaningful insight, to be honest with you, beyond that. It's the way it works out. That's the reason I can't give you a meaningful insight possibly means that I don't understand it well enough. But what it is that it really goes back to those coefficients and look at it. It's basically an algebraic relationship. Question?
Since you only need one pole on the right side, if you have one sign change.
Right. If your only purpose is to determine if it's stable or not, as soon as you see the first sign change, you can stop. You know it's unstable. But it gives you more information, because if you look at it, you will see that it gives you how many you have, actually. Now, it actually gives you even more than that. If anything becomes 0 here, what do you think that means? If you go to a 0, not a sign change, but a 0 in between. The other ones can be non-zero, but one of them can go to 0 all of a sudden. What do you think that means? Garrett? Yes. It means a pole on the j omega axis. So you can actually see, it's a way of determining where things are. You know, Jennifer, kind of like, let me answer this question. So it's kind of like, why is determinant defined the way it is? For example, if I ask you, right? For let's say 2 by 2 determinant. You're trying to solve 2 equations, 2 unknown. Part of it comes from the algebra of it. So I'm thinking about what's the better way to answer your question. I think that it really comes about the way that this product is calculated when you write it in the most general form. But now, the good news is, the interesting news is that this is actually probably the most rudimentary, the most basic criterion for stability, the most lowest level thing. There are a lot of other criteria. So a lot of times you actually don't have, when you have a system, a lot of times you don't have its transfer function, its closed forms. Right? When you're doing things numerically, it doesn't necessarily give you a transfer function in the closed form of this form. So you need to have other ways. There are graphical ways, which are essentially tantamount to this, applying this in a graphical. For example, Nyquist criterion. Nyquist criterion is different from Nyquist theorem for sampling. They're two different things. So Nyquist criterion is a way of looking at it. So essentially, in a Nyquist criterion, you can look at the trajectory of, so you look at your transfer function, for example, and you look at its value for j omega, as you increase j omega from 0 to infinity, and it goes through a certain trajectory in the plane, in the S-plane. And then you look at, there's a particular point, point -1. The criterion for stability is that you do not encircle that point. So this is stable, but then this is unstable because you're going around it. And this is marginally stable. If you cross this line but you come back before it. And the number of times you encircle it is equal to the number of right half plane poles that you have. And you can prove that. You can prove that through complex. It's a pretty simple proof. Actually, I do that usually in the 114. I prove it. So it's a simple proof that with the complex numbers. If you're interested in that, you can watch those tapes. And there are other criteria for stability, which even apply to nonlinear systems, like, for example, graphical representation, like circle criterion, or off-axis circle criterion, which basically is a generalization of this to the nonlinear systems. And there are lots of things, people who make their careers out of these, or made their careers out of these in the past. Any questions? No? So stability is an important concept. It's more important to understand the concept. I mean, you will probably do one or two of these exercises. And the key point that should stay with you 10 years from now is not exact details of Hurwitz algorithm. It's that there is such algorithm. That's the one that should stay with you. And the concept of stability, the way we derived it, you define something that's meaningful, and then you go and look at the mathematical way to describe it and find what are the criteria for achieving that. Okay? No questions? Let's take a quick break.